All right, I'm going to share my screen here. All right, so everybody should now be able to see my screen. And what I'm charged with doing here is talking about basically what we call here everything but NP and K, because we talked about that last week. And I was asked to talk just briefly about CEC. There was a question from last week that I'd like to clear up. And the question was, will the recommendation to eliminate the maintenance fertilizer phosphate and/or potash rates, 30 pounds P2O5 or 30 pounds K2O per acre, will that be shown on UK Regulatory Services soil test lab reports? And the answer to that is no, because in fact, the recommendation is temporary. It's just because of the situation we're in with prices, and we just can't justify maintenance if that's all it's going to be. In a more normal pricing situation, UK still has the philosophy that in the range of soil test report results that these fall in, that we would recommend at least a bit of maintenance fertilizer to keep your soil test levels adequate. In the example I had, which was one from soybean, and this is the new report form, the area here that's highlighted in green right here is the area where at 50 pounds of soil test P per acre, that's the maintenance rate. That will appear, but what we're telling you is when that appears at 30 P2O5 or 30 K2O for this year, or for now, we're not recommending you go forward with that. And this is the region within AGR1, table 15 for soybean that shows that. The 50 falls right here in the middle. On the left, we've got the soil test result, falls in the middle of this range. 30 P2O5 is recommended, and they're saying, let's not do that for now. The columns to the right have the soil test result for potassium that result in a K2O rate recommendation of 30 pounds of K2O. And again, we're saying when you're in that range, we're not recommending that you make a maintenance K application either. Now, the major thing we're going to be talking about this evening is we're going to be talking about secondary macronutrients and the micronutrients. Now, secondary macronutrients include calcium, magnesium, and sulfur. I'm going to focus on magnesium and sulfur because, frankly, I've never seen a calcium deficiency anywhere in Kentucky. I've seen some calcium deficiencies in Africa on really acid soils, but I've never seen them here. When we come to the micronutrients, I'm going to focus on the ones we know are a problem, or at least we're making recommendations for in certain crops. That's boron, manganese, molybdenum, some people just call it moly, and zinc. So those are the ones I'm going to focus on for the talk this evening. Now, the reason the macronutrients are called secondary is simply because, frankly, there are many fewer deficiencies in these. They are typically of secondary importance relative to the primary macronutrients, which are nitrogen, phosphorus, and potassium. Now, to get a handle on calcium and magnesium, ultimately I'm going to focus here a little bit more on magnesium. These are cations, and the way in which they cycle in the soil environment is pretty similar, at least in a general sense. We have a number of inputs coming in, whether it's residue, manure, or biosolids, one on the left, and on the right we have fertilizer or lime. They don't mention lime here, but in fact, that's an important source of both calcium and magnesium in Kentucky. And then we have some crop removal occurring at the top. Plants take up calcium and magnesium from the soil solution. They don't take up whole molecules like a whole gypsum molecule or a whole calcium carbonate molecule. They take up the dissolved ion that's in the solution. Now, that dissolved ion concentration is achieved as a result of either adsorption or desorption from clay over here on the right, the exchangeable phase. It can come slowly. The arrows are smaller from the dissolution, the dissolving of secondary calcium and magnesium minerals. And it can also come from some of the primary minerals in soils that are young soils and still have primary minerals that are left to weather. But the process of weathering, Kentucky soils are medium age or older, moves the minerals that contain calcium and magnesium, like serpentine, moves them to the right to form secondary minerals. And then finally, with weathering, you just have clays holding on some of the cations. The calcium comes from a non-exchangeable mineral, relatively abundant, called anorthite. It's a calcium aluminosilicate. It's found in the sand and silt fractions, particularly in younger soils. It's also found in feldspars, limestone, and apatite. Calcium is found there, and it's released again by weathering. Most of the calcium that's in equilibrium with what you find in solution is the exchangeable cation, calcium 2+. It is strongly held, and it dominates the CEC of our soils, and also the cation exchange capacity of organic matter. There is much more exchangeable calcium in a soil than potassium. That's why plants selectively and actively absorb more potassium than calcium. Typical plant won't contain more than about 0.5% of calcium by weight of dry matter, but typically it'll have about 2% by weight of potassium. And remember, I talked about mass flow and diffusion. The reason it does that is because it actively sets up a diffusion gradient, a concentration gradient for potassium, but not for calcium. In solution, the dominant cation in most soil solutions, except for sodic soils, is calcium, and it's 2+. It is also the dominant cation lost from the soil when a leaching event occurs. Magnesium, it's a lower in percentage in the Earth's crust. It's a component of biotite, pyroxenes, olivine, and dolomite. Generally, all of these are fairly easily weatherable, and therefore magnesium is more readily lost, typically. You do have certain soils that have a lot of serpentine in them, and serpentine is a little less easily weatherable, and that serpentine contains a chunk of mag at the start. Magnesium as an exchangeable cation typically is held on 10 to 20% of the CEC, and it's held fairly strongly, almost as strongly as calcium. And again, solution, magnesium, is important and is lost to leaching, particularly in weathered, highly acid soils. We have some of these in southern Kentucky, like in Metcalfe County on the old Cumberland Plateau. The exchangeable calcium and magnesium that we measure by salt test are held on the cation exchange capacity, and they are the primary agronomic form of these two elements that we consider plants to be using. The solution levels can be high in many soils, and they can be lowish in other soils, but in our soils, typically, they are more than adequate to provide plant nutrition. The other major source that we get these from is when we lime to control soil acidity, and as the lime dissolves, the basic carbonate is what neutralizes the acidity, and what gets left behind is the calcium and magnesium cations, which then occupy the cation exchange sites that the hydrogen once held before it was neutralized by the base in the lime. Calcium and magnesium are not bases. They do not neutralize acidity. They are merely exchangeable cations that replace that hydrogen once it is neutralized to form water and CO2. In Kentucky, calcium deficiency in our forage and row crops is unknown, and magnesium deficiency, which I'm going to talk a minute about here, is quite rare. Calcium is not very mobile in the plant, and if you were to see a deficiency symptom, it would occur in the meristematic, the youngest growth. We do have some challenges in some of our horticultural crops. I've seen this problem in brassica, particularly broccoli in my case, but it also occurs in cabbage, celery, and peanuts. Fruit quality in Michigan, where I was raised, the quality of apples is very much impacted by a lack of calcium. Tomatoes, blossom end rot tomatoes can be a problem without calcium, and watermelon also will have a poor quality if it doesn't have enough calcium. Again, it's rarely deficient except when the soil parent material is very acid, low in calcium, or both. This is a sugar beet plant suffering from calcium deficiency. You'll notice here in the center, these very burnt back, youngest tissue here, very poor doer, and it won't make much of a beet with that. This is from Africa. This is from South Africa, and this is a photograph of corn with a severe calcium deficiency on an otherwise very acid, sandy soil. So it's really a difficult soil to grow a good crop on because it's hard to get lime in this part of the world. And this corn is suffering miserably because of a calcium deficiency. This is blossom end rot in tomato, which is also associated with calcium deficiency. I see this more in certain horticultural environments like pot and pot and things like that, raised beds where they didn't do a good job of maintaining a good pH than I have ever seen in a field tomato environment. Magnesium, because it's more mobile within the plant, magnesium deficiency occurs in the older leaves. You have a nutrient that's mobile in the tissue, so the plant tries to move it from old tissue to young tissue in order to keep that plant growing when it's otherwise a little bit short. Plants that are really small, you may see the whole plant looks deficient. The leaves tend to show an interveinal yellowing, and the problem with that is we've got a lot of other nutrient deficiencies that look similar. Manganese, zinc in some cases show similar symptoms. In Kentucky, it has been observed on sandy soils that are acid and when the soil test is less than about 60 pounds, although that's not always true. The deficiency is more common on a worldwide basis than calcium, but is rare relative to potassium. In Kentucky, our biggest problem with magnesium is in the spring of the year, particularly on fescue, we have low forage magnesium concentration, and that causes grass tutney or hypomagnesemia in Kentucky cattle. And that's not due necessarily to low soil test mag, it's due to the low soil temps, and the fescue preferentially takes up either potassium or ammonium over magnesium at that time of the year. And then grazing, particularly lactating cows, will have a problem in that the diet just doesn't have enough mag for them. In a review of the literature that I actually did just prior to this talk, I was able to go back to 1960 when we have a documented magnesium deficiency in one cornfield and one tobacco field. The cornfield was in Wolfe County, and I don't know where the tobacco field was because all I got was a summary of some old work, and I can't tell you where it was located. Both of those fields tested less than 50 pounds of magnesium per acre. This is what magnesium deficiency looks like on broccoli. Some home gardeners may run into this in rare instances. Corn, this is an interesting situation where the soil here was really acid. I happen to know where this picture was taken, but you can see it's reddish at the edges and interveinal yellowing throughout. And this is a magnesium deficiency on an acid sandy soil. This is one that's not sandy. It's a no-till environment. It turned out it was magnesium deficiency. It's a little bit stunted too. And it's kind of generally pale. It's not, the younger leaves are dying. You can see some of these are dying here, but it's still generally pale all the way up to the leaf coming out of the whorl, which means it's pretty severe. This one, I don't know where it was taken, but I do know that it's a significant magnesium deficiency. Something this severe isn't going to do very well later in the season. Now I'm going to move on to sulfur. Sulfur is an emerging issue, and sulfur is interesting because it's available to the plant as an anion. This SO4 here in solution is the part the plant takes up. Now sulfate, if you look at sulfate, it lies right in the middle between phosphate and nitrate. Nitrate nitrogen is entirely derived from biological activity on residues and then transformations of ammonium to nitrate. Sulfate is partially and significantly affected by readily decomposable residues, microbial biomass, and there's a lot of sulfur coming out of that stable organic matter. But it's also significantly absorbed on some Kentucky soils to clay particles. It's adsorbed to what's called the anion exchange capacity. And that makes sulfur kind of in the middle ground where it's got a very significant organic component to its release from organic matter and organic residues. And it's also got a very significant inorganic component where you've got a cation, that is adsorbed to clay particles that have a positive charge. In Kentucky, these are typically those subsoils that are red to reddish brown. They have enough iron oxide in them. And at the pHs we normally have in our soil, there are certain parts of that iron oxide that are positively charged. There are places in Kentucky where one of the reasons people can apply anhydrous ammonia 3 weeks before corn planting without an inhibitor is because the nitrate that's formed in that 3 weeks gets hung on anion exchange sites in those reddish subsoils. This is true of Baxter's, Kreider's, and Pembroke's and soils like that. Now, it's not a permanent hang up, but it's good for the length of time it takes for young plants to form roots. Phosphate, on the other hand, is way over here to the left. It's almost all inorganic chemistry. There's a little bit of phosphorus that comes out of the organic matter, but it's not very consequential relative to all these other pathways by which it's made available. Mineral forms of sulfur depend on soil drainage. In aerobic and well-drained soils, you have sulfur in organic matter and it's released as a sulfate anion. In anaerobic soils, like wetlands and some poorly drained soils, you have some of the sulfur in organic matter and some of it's in sulfide minerals, like pyrite. And that can be as or more important than organic S in those soils. The exposed pyrite will oxidize. So when the wetland is drained, you get pyrite oxidation and you form iron sulfate plus additional acid. This occurs in both mine spoils and drained marshlands. It is adsorbed, as I said, as an anion. It's held on kaolinite and aluminum iron oxide clays, especially low pH in Kentucky, and especially the red to reddish brown subsoils. Hydroxyl is actually its strongest competitor. So you get release of sulfate as the soil pH rises with liming, assuming there's any sulfate there. That occurs in the surface because lime reactions don't move down very rapidly, but the sulfate then moves into the subsoil. And we're starting to get suspicious that the reason we're not predicting sulfur response very well in Kentucky is because our producers are taking primarily surface samples, and they need to take a subsurface sample in order to assess the sulfate status. In Georgia, where they grow a lot of onions, and the onions are a sulfur-loving crop, they typically recommend that they get a sulfur assay on the subsoil, which in some of them sandy soils means you have to get 2 feet down into them. That will give you a clue about whether you need any sulfate from gypsum or other fertilizer in order to meet the needs. Other factors are important to adsorb sulfur. You have to have a certain amount of this clay. You can't get by with a coarse silty material, and the soil texture is like a coarse silt loam. In the soil organic matter, it matters whether the organic matter has a high C to S ratio or a low C to S ratio. If you have a low C to S ratio, the residue as it decomposes will release sulfur from microbial activity. But if it has a high C to S ratio, the opposite occurs. You get immobilization of your active inorganic sulfate, and you will see less sulfur in solution. Anions can be serious competitors, and they can push sulfate into the solution. Not just hydroxyl, but phosphate will do it. But nitrate and chloride are down in the pile a little bit farther, and they're not as able to push sulfate into solution. Sulfate is what we call moderately mobile in many Kentucky soils. It will leach slowly, but it will leach and leach out of the root zone. The soil solution anion is the most important form, although there are certain ion pair species that are important under certain conditions. CaSO4, the uncharged monomer, and aluminum sulfate plus are also important in certain situations. And this sulfate ion is the one that's lost when leaching does occur. With the organic sulfur, generally mineralization is occurring if the C to S ratio is less than 200 to 1 on a dry matter basis. and immobilization occurs if the C to S ratio is greater than 400 to 1 on a mass balanced dry matter basis. Mineralization is favored by warm but not hot temperatures, moist but not overly wet soil, and a near neutral pH value. We see sulfur deficiencies, temporary deficiencies in Kentucky on cool season grasses occasionally. Wheat is becoming a larger issue, and we think we're starting to see some lower tissue levels in alfalfa, at least for the first cutting. We've not been as successful getting responses on the warm season annuals, corn, soybean, but we're still looking. Organic sulfur does fall and decline as organic matter falls and declines with years of cultivation. The more you've cultivated a soil, the C to N to S ratio narrows, indicating that the organic sulfur is more resistant to being lost than organic carbon and nitrogen, but it's still depleted over time. There's a particular enzyme that can be tested for. It's called the sulfatase enzyme, and it's important because it's the one that hydrolyzes these organic sulfur esters, and those can constitute more than 50% of the total topsoil sulfur. But when that mineralization occurs again, you get sulfate released, and that's the form you find from organic matter. Atmospheric deposition of SOX compounds are a declining source, still important for many crops, but it's declining in its magnitude. SO2 is a particular SOX form that reacts with both oxygen and water to give sulfuric acid. That dissolves in rainfall and falls with it. You can also get direct absorption of CO2 by plant leaves. When that happens, if you get too much, it'll actually kind of fumigate the plant and you'll get damage. But in lower quantities, it acts like a foliar atmospheric fertilizer. As I said, atmospheric deposition of sulfur is decreasing. This graph shows the situation in pounds of sulfur being deposited in 1994 per year. This 1994 data was released by the National Atmospheric Deposition Program. Now you can see that Kentucky was kind of in a hot spot where you had a lot of sulfur deposition because of the number of coal-fired power plants that were in the state. But by the 2009, we're still a better spot than some, but decommissioning had really reduced the amount of sulfur deposition, and it's gone down even further because now it's been another 13 years, and even Paradise is being decommissioned now. And Paradise was legally emitting around 10,000 tons of sulfur per year. Sulfur deficiency is still relatively rare in Kentucky, and we are actively looking because we know it's an emerging issue. It's not very mobile in the plant, so early deficiencies typically involve younger tissues, maybe the whole plant. You get stunting. Sulfur is a part of the chlorophyll process, so you get generally pale green to yellow tissue colors. Our worst problems are on coarse sandy, coarse silty soils that are low in organic matter, soils without a history of fertilization with sulfur-containing materials. We never see a sulfur deficiency on a tobacco soil that's been kept fertilized with potassium sulfate. There's plenty of sulfate or sulfur around. In the old days, when ordinary superphosphate was used, O20O, there was a lot of gypsum in that product, and that also meant that sulfur was widely available from the use of that. That has fallen off, of course, because we're now using triple super, DAP, and things like that. But K-sulfate is a material that has been used, particularly with tobacco, and means those fields are unlikely to ever see a sulfur deficiency for another 5-10 years. This is sulfur deficiency in corn. You can see, even though the plant is generally pale green, the central leaves, the younger leaves, are the ones that are showing the worst deficiency symptoms. This is what it looks like when you can see the stunting. It's stunted downward. You don't get a lot of node elongation, so it looks like it's being pushed downward. And again, it's really pale at the top, center, youngest tissues in the plant. This is another example with a tomato in a pot. deliberately grown to have sulfur deficiency. Again, you see this general stunting and general yellow color, and particularly on the youngest leaves. Now I'm going to return to this slide, which I talked about last week. There are three ways by which nutrients come to be at the root surface. Sometimes the root finds them as it explores the soil. That's called root interception. But the other major ways are movement of nutrients to the root surface. One of them is mass flow, and one of them is diffusion. Mass flow is associated with very mobile, not in the plant now, in the soil solution forms, and they move with the water that is already headed to the root. Diffusion is associated with less mobile, even immobile nutrient forms, and the root works. It actually creates a concentration gradient, causes that diffusion. That's particularly important for phosphate and potassium. Now, we have soil mobile nutrients like calcium and magnesium cations and sulfur anions, and they are going to be extracted from the larger soil volume by mass flow, this larger area around this root system. Whereas the immobile nutrients like phosphate and potassium are absorbed in these little zones, these little absorption zones that surround the individual roots, or maybe even the fungal hyphae of mycorrhiza that have formed an association. So what we're saying here is that calcium, magnesium, and sulfur as secondary macronutrients are being extracted from a much bigger volume of soil because they're moving with the water that is moving to these roots because of transpiration, pulling the water into the plant, and then it's exiting through the stomata. This is an example of the amount of different macronutrients that arrives at the root surfaces of a pretty good corn crop. This is about 150 bushel corn on a fertile alpha sol. We have a lot of alpha sols in Kentucky. And it's pretty clear here. We've got the amount that's absorbed in kilograms per hectare and then pounds per acre in the first two columns here. Then we have what arrives by root interception. And you can see of the amount that's needed, the amount absorbed, which is about 40 kg per hectare, we're getting 60 just from root growth alone. So unless you have a compaction problem, you will more than get enough just from the roots exploring the soil. That's not true for magnesium or for sulfur. On the other hand, mass flow, the movement of these with the water, because of their concentration in the average soil solution, you get more than enough arriving at the root. There's nothing left to diffusion, and you get plenty of calcium, magnesium, and sulfur by that pathway. So the mass flow presents enough of these three secondary nutrients to the root surface. Now, at that point, root uptake can be both active, and it is, meaning they've got active enzymes that are pumping those cations and anions across the surface. That's true for magnesium and sulfur. Or passive. Passive means there are pathways, typically close to the root tip, where the ions can pass freely into the vascular tissue because transpiration is pulling them. And the active one is driven by the plant doing respiration, doing work, but the passive one is just by transpiration. So it's pretty clear that calcium pretty much always comes in passively, but magnesium and sulfur may come in both active and passive. There are almost all plants contain enzymes that will pull magnesium and sulfur into the plant. Nutrient needs vary a lot by crop. 200 bushel corn, 70 bushel soybean needs more calcium particularly. Grass hay, 3.5 ton, doesn't contain as much as an alfalfa hay crop at 5 ton. And much of these needs, in Kentucky anyway, can be met by the soil. It's not perfect. There are going to be situations where it won't work out, but I've never seen a calcium deficiency on any of these crops, so that's been plentiful. Magnesium is really rare, and sulfur is fairly rare to see a deficiency. Now, last week there was a question about sulfur in soybean. So I went back and I looked at UK data because I the old guy, so I get a lot of stuff sent to me and I accumulate it. And I looked at 2 time periods. One was from 07 to 12, and the other one was from 13 to 20. In the first period, there were 23 soybean studies on out of 12 on research farms. And on the second period, there were 25 studies out of 25, and they were all on research farms. Sorry, 12 were on research farms in the first period. That means the other 11 studies were on grower farms. All of these had a -S check versus a +S added sulfur material. Now, added S in these studies, because some of the investigators had other objectives than just looking at sulfur as a nutrient, ranged from 10 to 800 pounds of sulfur per acre. Interestingly enough, the 800 pounds didn't hurt anything, but it was pretty clear they were looking to get greater root growth on a fragipan soil, and it didn't work. The sulfur sources that were used range quite widely. Some people use gypsum. That was pretty common. A little bit of ammonium sulfate, a couple treatments with potassium treatment, and there was one experiment where they were looking at sulfomag, sulfate of potash magnesia. The sulfur treatment yield of the control, the -S treatment for soybean, ranged from about 45 to about 85 bushels per acre. In the first period, the yield response to sulfur addition ranged from a -12% to a +18%. And in the second period was a narrower range from -6 to +14. Now you might ask, well, how do you put these together? You don't average them because you really need to understand how these are distributed. If that -12 is just one of them and a +18 is just one, they don't mean nearly as much as if there's a few other out there with them. So what we have here is a cumulative frequency versus the +S response, which is a percent of the -S yield. The 0 here is in the middle, and the 50% point is the horizontal dark line in the center. The dark diamonds represent the first period between 2007 and 2012, all different locations. This is the one that has a big spread. I've got 4 locations here where there was a yield loss of 5% or greater, 4 out of 23. Most of them fall between -5 and +5, and they cross over here at about +1%. They also, in that group, they had 3 that were above 5% in yield response. Now, you can say whatever you want about soybeans needing sulfur, but just by the luck of the draw, you can have about as much of a chance of having a negative yield, serious negative yield, as having a serious positive yield. Now, the next time period, all of these are on research farms. And again, you've got some spread. Got a couple here right close to a -5%. The bulk of them are in this region between about -1 to about +6. And then I've got a couple that are up here, really nice, 10 to 15%. The real question is, what is your odds? The median frequency, this is the median, says I'm going to be right here about 2 to 2.5%. So that tells you I've got a decent probability of getting at least 2.5% yield, 2 to 2.5%. By the way, I gave these individual here, like in the first period, there were 2 really negative, none in the second period, 2 that are moderately negative, 1 in the second period. But that's what these numbers here mean. So a lot of these high probability events are located between somewhere about -3 to 4% and plus about 3 to 5%. That's where the big events are. But there has been clearly a shift. This data was not as promising for sulfur on soybean. This data is more promising, but it's pretty clear we have a ways to go before we get a lot of drama. So the sulfur response has shifted to the right, and a positive response is now more likely. The median rose from about 0.8% to about 2%, and the negative yield responses were reduced from 10 out of 23 to 6 out of 25. If we look at just the research farm data in the first period, the 12 trials, the median rose from about negative 1.8% in the first period to 2% in the second period. That is a big jump. That's a 4% shift. It accounts for why, as I said earlier last week, we don't think there's a lot of drama for soybean. But when you look at the data, there's clearly been a shift, and there's probably going to be a shift going forward. As we deplete sulfur in the soil, we don't replace it, we leach some of it away, we're going to see more positive responses in soybean and probably in corn as well. But the amount is still relatively small. 2% of 45 bushel beans is 0.9 bushels per acre, and 2% of 85 bushel beans is 1.7 bushels per acre. Even at $15 beans, you don't have a lot of dollars to both buy and apply 10, 15 pounds of sulfur, particularly if you use more expensive sources like ammonium sulfate, sulfomag, and potassium sulfate. If you're going to use gypsum, you might cover your cost. The second period data is also much more spatially limited. We're strictly on research fields. They don't get sulfur fertilization routinely. They're now getting less sulfur deposition. These fields, by the way, do have less erosion in them and somewhat greater organic matter than the state average. So we're really working in an organic matter environment where that organic matter returning residues are probably less sulfur in them as the grain is removed from these fields. Now, the basis for correcting deficiencies of these three secondary macronutrients depend partly on soil test and partly on plant tissue analysis. Soil tests for calcium and magnesium, we do them routinely, but they're generally not helpful except when magnesium is very low. And part of the issue is if you maintain the pH, they rarely will get very low. Soil tests, especially subsulfur S, exist in other states and regions, but it's not yet officially recommended in Kentucky because we don't have a correlation. We can't tell you exactly where subsoil S needs to be, so we don't recommend fertilizer. That's one of the areas of active research at present. The tissue test, doing a routine plant tissue analysis, is often when we see these problems being first detected, whether it's wheat, alfalfa, fescue, whatever it is. Growers will submit a sample or a consultant will take a sample, and that's when we find it. And then we do some other things and start looking at adding sulfur in these particular cases. We haven't caught anything with magnesium this way, but we have caught sulfur with our tissue test surveys. If you need calcium, acidity management in Kentucky provides the needed calcium. In horticulture, some crops like tomatoes growing on sandy environments will require some supplementation with more soluble sources like gypsum. Magnesium, again, acidity management for soils that are low in pH also calls for dolomite. But interestingly enough, even good ag lime that's mostly calcitic contains 1 to 2% magnesium by weight. And when you're putting on a couple tons per acre, you're putting on a significant amount of mag. So it's not clear that as long as we're doing a reasonable job with the calcite we have, that we're not pretty much doing a reasonable job of magnesium application. Another thing is true is that very little magnesium is removed in the grain. Very little calcium is removed in the grain. It's crops like alfalfa where you're going to be removing more calcium and more magnesium in the crop. And if that doesn't come back to the field in terms of manure, you'll potentially over time have less of these materials less of these elements in the soil. Sulfate salts of magnesium, of which the best one is sulfomag, although Epsom salts is available, they can be used, but they are expensive and are not usually recommended relative to applying dolomite. Sulfur, correcting deficiencies, there's a wide array of products that are available. As I said earlier, we've got a number of fertilizer materials that contain sulfur: ammonium sulfate, calcium sulfate, elemental sulfur, potassium sulfate, sulfomag, potassium magnesium sulfate. A typical application rate is 10 to 25 pounds of sulfur per acre. If you're going to use 25, you probably won't need it for another 2 to 3 years. And very little is needed for most crops. And frankly, at this point, there's very little need. I know there are a lot of growers that are applying sulfur prophylactically. And I think if you can get it really cheap, go ahead. Gypsum or calcium sulfate is probably the most widely available cheap source. You can get it as a byproduct of power plants. You can get it as a byproduct of water treatment plants. They even grind up old waste drywall, because drywall, what's in it is gypsum, and they sell that. Elemental sulfur is probably the poorest choice because it's elemental. It has to be oxidized by microbiology. Thiobacillus ferrooxidans has to work on it, and it's slow. It's typically 90 to 99% sulfur by weight. It has to be ground very fine to work, which means it's not very compatible in bulk blends, but it is out there. It is being used. Just remember that you have to apply more because you're not going to get a lot of sulfate out of it, and elemental sulfur itself is not available to the plant. It has to be oxidized to sulfate before it's available. I'm going to leave the macronutrients and move on to the micronutrients. Micronutrients come in a kind of funny classification. The ones that are considered essential, all or most plants cannot complete their life cycle without the element. The first 6, zinc, copper, iron, manganese, boron, and molybdenum, have been known for many years. The red circles denote the ones that have been seen as problems in Kentucky. Chloride was identified in 54. Nickel was identified in 87. These are for all plants. We now know that vanadium, sodium, cobalt, and silicon are required by some plants, but not all. So they're essential, but not for all plants. Then we have some where plants contain these, and they're needed not by the plants, but by animals that are consuming that plant material. They're not essential, and as long as the concentrations are fairly low, they're not toxic. Cobalt, chromium, selenium, iodine, and tin are 5 of these. The ones in red, indeed, zinc, manganese, boron, and molybdenum are the deficiencies we've seen on occasion in Kentucky. The other problem with these things is they can become toxic if they're taken up too high. They can be toxic to the plant, or they can be toxic to the animals consuming them. Particularly the ones that are toxic to animals consuming them, including the human animal, are mercury, lead, and cadmium. You can observe excess amounts of otherwise innocuous, even beneficial elements with things like chromium, selenium, nickel, sodium, zinc, copper, manganese, boron, molybdenum, and chlorine. So you can get to a high level that causes problems for the plant or for animals consuming that plant. I've seen boron toxicity out west, and it looks pretty bad. It's can't grow anything because you can't hardly get it out of the soil once it's at a high level. This general cycle applies to all the microelements. It's just that you have to remember some of these boxes are technically more important than others for certain of the elements. But in general, you have soluble salts and mineral weathering that release these as ions into the soil solution. Some of them form complexes. Rainfall carries in things like when it rains out of the Gulf, we get chlorine and iodine from Gulf rainfall here in Kentucky. Iodine is important because it prevents goiter in humans. If you go to the West where they don't get enough rainfall with an ocean origin, they have a problem more with goiter. At least they did in the old days before iodized salt became commonplace. Some are adsorbed onto clays and iron aluminum oxides, and that means they're held against leaching, because leaching is the way most of these are lost over time, and old soils tend to be depleted of many of the micronutrients. Organic matter can play a role in absorbing things like copper and manganese. So the organic matter holds on to these and again, holds them against leaching losses. And then finally, they're removed from the soil solution by plant adsorption. Sometimes you get a bit of reduction at the root. and then you get incorporation into the organic matter when that happens. There's a group of these that are cations: iron, zinc, copper, manganese, and nickel. And they do a lot of different things in the plant. Iron is important, particularly in photosynthesis. Zinc for enzyme activities and hormone synthesis, a lot of disease resistance. Copper is involved in photosynthesis. Manganese is involved in photosynthesis and also lignin synthesis. And it was discovered that nickel is an important constituent of the urides and therefore has a major impact in nitrogen metabolism, but it is really only needed at really trace levels, but it is needed. Anions, boron forms borate, chloride, and then you have molybdate. And you can see they play important roles. Boron is really important for pollen tubes in corn and sugar and water translocation. When you have dry weather and you don't have adequate boron, you'll have even worse corn pollination than you would without boron. Chlorine is, I've never seen a chloride deficiency, but I'm told that it matters in terms of cell turgor and photosynthesis. Molybdenum plays a role in tobacco nutrition. John Sims did some work here, and now a lot of the setter water formulas that are used in Kentucky for burley, particularly, but also for dark, contain molybdenum because it's important for nitrate reductase, which is the first step towards synthesizing proteins to take nitrate and reduce it to something that has less oxidation. Micronutrient deficiencies are ID'd, but they're very challenging because they often look alike. You need to know the nutrients' role in crop physiology, growth, and development to kind of pinpoint where you should be looking. And when you see a symptom, that helps you understand at least what some of your options are. To make the deficiency symptom analysis work for you, you have to know each of the crops you're looking at, and it works better in association with a knowledge of soil properties. What's the parent material? What's the mineralogy of the soil? What's the pH? What's the redox? Is it a wet-natured soil that's saturated, or is it a well-drained soil that's aerated? Soil organic matter levels, and etc. Zinc deficiency is associated with eroded, low organic matter, cold soils that are high in pH and or phosphorus, or with really acid sandy soils that are low in soil organic matter. The only place I've seen it with any great regularity in Kentucky is corn. And you see it in the central bluegrass because you have high enough pH and really high phosphate levels in these soils. Symptoms occur on younger or on small plants, all the tissue, and you get really short internodes. And if you take a knife, split the plant, you get these dark colored nodes when you split it apart. It's stunty to the point of looking bushy, and it's rosetting. Depending on the hybrid, you get leaf interveinal chlorosis or maybe a total whitening of a portion of these younger leaves. And the problem with zinc is you can have a 10 or 15% yield loss and it won't even give you a symptom. That's called hidden hunger. Plant needs it, but it's not giving you a deficiency symptom. This is an example where it's sharply rosetted here. I mean, this is really stunted through the plant here. And we've got this bleaching out, turning whitening on portions of these younger leaves. But this hybrid, it's also zinc deficient, and it shows this interveinal chlorosis. The neat thing about zinc is, with all the other nutrients, it'll be every intervein itself. But with zinc, you get this irregularity, you get skips. And that is kind of symptomatic of zinc relative to something like manganese or magnesium, which also cause interveinal chlorosis. But this thing also shows rosetting. It's really a stunted plant. All the nodes are very close to the ground. Manganese deficiency is typical in Kentucky on really high pH soils that are low in native manganese minerals. I see it on the Ohio river bottoms, in soybean particularly. Soil pH is at 7.2 to 7.8. Manganese can actually be toxic in low pH soils below 5.5 that are high in manganese minerals. In Kentucky, the deficiencies occur in soybean and the toxicities occur in tobacco. There's a lot of tobacco fields that during the season, they drop in pH and they drop into a region where manganese is soluble, and you start seeing manganese toxicity. Symptoms are typically on the youngest or all tissues, and it's an interveinal chlorosis or a gray oval spot, leaf speck on the edge. That's the deficiency symptom. We also notice that root disease and rots are more prevalent with manganese deficiency. And again, symptoms are not always visible. This is manganese deficient soybean. It has pronounced interveinal chlorosis, and it's a pattern over all the leaves that are affected. You don't get skipping here. This is a field environment. This is taken from a river bottom, and you can see these, it's in areas. And when we probe this, all the really yellow areas were really high pH, 7, 8. Whereas you get into the green areas and it drops down around 7. So the manganese solubility was just so low at the high pH, the crop couldn't recover the manganese and it suffered dramatically. Now, in some crops like grain sorghum, they've actively done some breeding to help make this a little better. And those high varieties do better when manganese deficiency is around, but they don't yield as well when there's no manganese deficiency around. So they're only used in areas where it's an ongoing problem. Boron deficiency is typically caused by low boron parent material, meaning it's low in tourmaline. Tourmaline is the mineral that contains boron out there in the soil. It's also associated with low soil organic matter because a lot of boron cycles inside residues, and as time goes on, you keep removing it at very low rates, but you remove it and you get a low organic matter, a low organic boron situation. It's also a problem when you have a recently limed acid soil where you got the pH too high, and it's also a bigger problem when it's too dry because boron tends to move by mass flow into the plant. So if it gets too dry, the plant won't get enough. I've seen boron deficiency in several fields in Kentucky, usually in corn, but others have seen it in hay, alfalfa for hay, clover for seed, and soybean. It's moved in the vascular tissue, but it's not remobilized. So symptoms always occur on the youngest tissues. You get a brittleness, a stem cracking, water, sugar transport. You get deformation or death of terminal tissues, and you end up with poor pollination. And you get reduced flowering and seed set in clover. Symptoms are not always visible with this nutrient either. This is boron deficient alfalfa. This was a really good shot that I got from University of Illinois Cooperative Extension website. And it gives a good, it turns yellow, reddish color between the veins. And then you've got some spotting in there as well. This is corn. When the corn is green, you get this kind of witch's broom look to it, but it's in the leaves. It's not in the tassels. It's all wrinkly and shriveled up because it's not doing a good job of getting boron to extend that tissue into space. In corn, the lower ear is the one that has significant boron deficiency because none of this pollinated. There wasn't enough boron to keep sugar and water moving to keep this thing turgid during a period of weather, where the upper ear had enough boron to make it happen. Molybdenum definitely occurs in Kentucky, and it occurs on low pH soils that are also low in native molybdenum. Interestingly enough, in soils, none of us know what the native molybdenum mineral really is. We just know that low total moly, you dissolve the whole soil up in acid, you get these soils that are low in moly. Now there's the flip side. Knobs soils, particularly things like a trappist, formed in Devonian shale, black shale soils, are high in native molybdenum. And if you overlime them, the forage becomes toxic to ruminants. You have high molybdenum in things like legumes. So you have to be careful with these kind of soils not to overlime them, keep them no higher than about 6 to 6.2. Deficiency has been observed in tobacco, soybean, and forage legumes. Symptoms occur on the oldest, sometimes all the tissue, but usually the oldest, and you get this pale green, yellow color because molybdenum is really critical to nitrogen metabolism in the plant. The leaves will sometimes cup in some species, they'll form a cup, and you get this death of tissue at the leaf edge, and you also get crop stunting. Got some pictures here. The upper one to the left is alfalfa. It's got a lot of different colors, but again, this is a molybdenum deficient plant, and it tends to be the whole plant. This is all the way to the top. Soybean that came from North Carolina State, and it's generally stunted. It's not very leafy, and the soil here was low in organic matter and low in moly as well. The cupping is most evident on cauliflower, which is the lower right. You can see dramatic cupping on the left part of that picture, and a nice big full leaf where the molybdenum was more available to the right. The basis for correcting deficiencies depends on the micronutrient in question. UK offers soil tests for boron as a separate request, and we now do zinc routinely as long as you ask for the routine test offered by UK. That's the one that you also get phosphorus, calcium, magnesium, and potassium. We have no soil tests for manganese and molybdenum that are routinely available, and therefore plant tissue analysis is about the only choice you have if you suspect manganese or molybdenum. A lot of people know these areas. I know growers in the Ohio River, and they know exactly where these fields are, and they get their foliar manganese out right from the get-go, and they're ready to go to put it on 2 or 3 times during the season. But when they rent land, they sometimes don't know, and they run into problems, and they have to do a plant tissue analysis to confirm. Tobacco people normally just use moly in the setter water and just avoid the problem. For a time, molybdenum was offered for soybean as a seed treatment, but it was hurting the rhizobium. Now, because many soybean fields have been in soybean often enough, you don't need rhizobium every year with it. They can return to a seed treatment with moly. Sometimes they actually soak the seed in a little bit of a solution that contains molybdenum and then let the seed dry again so it flows better through the planter. And they have all the molybdenum the crop's going to need. But on these soils, you have to do it every time. Boron is often used prophylactically on alfalfa and whenever clover is grown for seed, which we don't have much of in Kentucky, but we have a lot of alfalfa for hay. I know producers that after every cutting, they're out there putting on a 1/4 pound of boron to make sure they don't have a deficiency for the next cutting. And that's not a bad thing as long as you make sure you don't run up, get too high a rate, make a mistake, and over boronate, you might say, a soil. Another way you can correct deficiencies is, again, maintain the right soil pH. Keep the acidity low, keep your pH between 6 and 7. Animal manure contains boron, by the way. Granubor is a dry source that you can use for 2x2 dry and bulk blends. It's very compatible. Solubor is a dry source that dissolves readily in liquid water-based materials and is often applied foliarly. It's also used in fertigation for those who irrigate. I had a producer in southern Kentucky who he lost 50 bushel an acre. He lost 50 bushel off the top of 280 bushel corn because none of the tips filled out. And he did have the leaf analysis. He just hadn't read it. And it showed low boron. And that was the clincher. He didn't have that problem again once he started to fertigate once a year ahead of tasseling with a boron product. Manganese, you have to avoid over-liming, or you can drive the pH above 7.2 to 7.3, and you're going to start seeing manganese problems. And you got to keep it above 5.5, or you'll have manganese toxicity on some soils. Manganese sulfate is a great dry source for 2x2 and blends. Manganese chelates, chlorides, nitrates, some sulfates also work as dry sources that dissolve. The problem with manganese sulfate is some is kind of a fertilizer that's got a lot of other things, kind of like little dirt in it, and it doesn't work very well for liquids. You have to have a really clean source. That manganese sulfate is going to be more expensive than the typical stuff you blend or use in 2x2 dry placement. Molybdenum, again, acidity management to keep the pH between 6 and 7 and avoid a pH above 6.5 for forages on the knob soils, okay? Or you can get molybdenum toxicity. Most moly is applied in setter water for tobacco, and the rest of it is either applied foliarly or seed treatments. You cannot apply it directly with rhizobium because it kills it. So ammonium and sodium molybdates will kill the rhizobium. So there are now some coating technologies where they apply a barrier between the rhizobium and the molybdenum so the molybdenum won't kill it. And I've worked with those. I'm not sure how successful they are, but they say they're quite successful. Make sure they are there if you're going to use seed treatments with rhizobium and with moly. Zinc, again, is one you want to avoid overliming because it drives the zinc availability downward. And you want to keep your pH between 7.2 and above 5.5 in this instance. Again, zinc sulfate and zinc oxysulfates are good dry sources for 2x2 blends. Zinc chelates, chlorides, and nitrates are good dry sources that are suitable for liquid and foliar application. There's a lot of zinc that goes on as liquids and foliars that works very well as long as you put on the right amount. Okay, this pretty much concludes the macronutrients and micronutrients portion, and then I've just got a slide or two on CEC. I was asked specifically to address what you can and can't do with CEC on your soil test report. The first thing you've got to understand is the lab does not determine CEC. They calculate it. They take the extractable calcium, magnesium, and potassium from malic 3, and they make an estimate of exchangeable hydrogen from pH and buffer pH, and then they calculate CEC. That gets to be a real problem when you've got recently lime soil and the malic 3, which contains acid, dissolves part of the limestone. You get really inflated numbers for calcium, magnesium, and a really inflated CEC. So you have to learn to take some of that with a grain of salt. Kentucky soils have a very narrow range actually in CEC relative to where I was raised. Michigan, it ranges from 3 to 30. And here it ranges between about 10 and 20. In fact, 85% of the soils in Kentucky that are sampled at the surface are either silt loams to silty clay loams, and the organic matter range is fairly narrow, 1.5 to 3.5%. So that's why the CEC, the normal CEC, is going to run in a fairly narrow range. Now, there are some interpretations you can do, and then there are some you can't do. When the CEC is low, that means you have less buffer capacity, so less lime is needed to raise the pH, but it also doesn't take as much N fertilizer to drop the pH, and because the soil is not well buffered, you will get more leaching losses if you over-apply things like potassium fertilizer. You just will have more leaching losses because you don't have as much to hold on to these cations. You can't do much with nitrogen or phosphorus management using CEC. It has little to no role to play. When I see a high CEC soil that looks real, in other words, it's not due to dissolving limestone, I sometimes realize that it might be a heavy clay that's kind of wet. Okay, that means maybe it'll have a role to play in nitrogen management, but that's a real backhandward way of getting at it. All you've got to do is check the drainage box on the soil test form in Kentucky, and we'll know what drainage we're working with. When the CEC is high and the soil is clay, and you're in the northern knobs, like in Owen or Grant counties, you may need more potassium for tobacco because we associate that high CEC with a mineral called illite. And that mineral really likes to fight the plant for potassium. And we were training, I don't know if we still are, Ken Wells was the last one I saw doing this. We were training agents in those counties to take a UK recommendation for potassium for tobacco and add 30 to 60 K2O to it in order to make it appropriate for that crop. Some of you may be aware of a philosophy called cation balance, where maybe an ideal soil has 65% Ca, 10% mag, and 5% potash on the exchange phase. That has been looked at time and time again, and it has no scientific merit. There is no ideal cation balance to shoot for using the CEC. So I'm going to close with a few things to avoid. Avoid prophylactic sulfur. Actually, in wheat, we've observed some significant yield losses above and beyond those few odd negatives that I showed you in the soybean data. We've seen some yield losses when subsoil sulfur was too high. They put on more sulfur and then got a significant yield decline. Avoid using calcium sulfate or gypsum to raise the calcium saturation of the CEC. Some people even haul in calcite when there's dolomite close by. Don't spend money on the additional diesel fuel. Adding more magnesium when the soil test is above 60 pounds. We've never seen a response. Again, some people haul dolomite a long distance in order to get more mag that way. It's probably not going to give much economic benefit. Avoid prophylactic boron or zinc unless you're doing a good job of monitoring plant tissue, because you can develop toxicities to either one of these two micronutrients. Avoid manganese or zinc oxide products. Oxysulfates for zinc are okay, but oxides are insoluble in many soils and don't give you enough bang for the buck. And then, of course, we have a group of chemical and biological fertilizer additives that, quote unquote, make the micronutrients more available. I've looked at some of these, other people have looked at these, and there isn't a single one that hasn't been called hooey by most of us when we're done. That being said, there are some new things that I really encourage producers to start getting more familiar with and start thinking about how to incorporate these into a nutrient management plan. Plant tissue analysis is a greatly underused tool. Learn how, when to take your samples, and then how to interpret the report results that you get. Boron. Start thinking about soil testing for boron. Consider adding about a ½ pound if the UK soil test is below a ½ pound. I've seen responses in corn. I haven't seen a good response in soybean. I admit, soybean seems to be a crop that doesn't respond much to boron, but it's a canary in the coal mine. If I foliar analyze, if I get a plant tissue analysis and I get a low boron test on a soybean crop, I'm going to recommend an application for the next corn crop because the soybean has given the situation away. If you can get your test done in time, you can use Solubor, applying it foliarly. It's compatible with a lot of other things, but you might want to do a jar test to be sure. If you do soil test for S, and especially on fields that you know have red-brown subsoil, take a topsoil and a subsoil below 8-inch sample. We don't know exactly what to tell you, but we do know it's unlikely you will need any sulfur if the subsoil test level is 15 pounds S per acre, 7.5 ppm or higher. So the take-home points I'm going to leave you with this evening are soil test, but use plant tissue analysis because it's important for these secondary macros and the micros. Again, always think about keeping your pH in the right place to improve nutrient availability, because many of these micronutrients, their solubility and availability is a function of pH. Keep it in that 6 to 7 region. If you still suspect a problem, use proven products that fit into your nutrient management plan. You might be able to find a way to put them in your pop-up. You might be able to find a way to put them in foliar. You might be able to find a way to blend them in. But there are good products out there that are proven. And avoid products that when you get a feeling they're too good to be true, they probably are. So I'm going to say thank you very much, and I'll stop and take a few questions. let Philip ramrod that situation.